Welcome back for the second lecture by Boaz Klartag for the Simon's lectures. So Boaz is still a high-dimensional geometer. It hasn't changed since yesterday. He has one thing I didn't mention yesterday is that he has received a number of prizes, including the European Math Society Prize, the Clay Research Fellowship, the Erdős Prize, and yesterday we saw how to pack high-dimensional oranges. Today we're going to see how to slice them.
Thank you so much. Yeah, you summarized my lecture very well. Thanks for the introduction, and also thanks, Michelle, for the wonderful hospitality. It's really a little heaven here at MIT. I really enjoy my time here. So indeed, I'm going to discuss high-dimensional geometry. We discuss geometry in n dimensions as dimension n tends to infinity. That's what we do in this lecture series. But it is slightly different geometry from the more familiar geometry in a fixed dimension, in dimension maybe 2 or 3. But it seems that perhaps one may develop some intuition here. And let me emphasize that we really care about depends on a dimension. Okay, so asymptotics really matter here, and we really make a big distinction between universal constant, just numbers, and constant depending on a dimension in this business. High-dimensional geometry has many successes, but for many years there also have been very, very simple questions that remain unsolved. And one of the main such questions was Bourgain's slicing problem from the 1980s. So the question is as follows. Suppose that you have a set in Rn, which is convex and has volume 1. Okay, you can think of a polytope, a Euclidean, whatever. Can you find a hyperplane section of that convex set whose volume is at least 1/1000 or some other universal constant? So apparently this question was unsolved for many years. And in some sense, it was the minimal, non-trivial open problem in this business. So there were like a bunch of conjectures much stronger, but even that question was beyond reach for many years. Let me tell you that if you don't ask for universal constant, but you allow dimension-dependent constant, this is much, much simpler. For instance, let me tell you how to get 1 over, a constant over square root of n under some mild assumption. So there is a reduction to centrally symmetric convex sets. You assume a point of symmetry. So how would you get constant over square root of n in the centrally symmetric case? What would you do? So you can look on the width. A convex set there are two formulations. Either that for each 2 points the segment is inside, or intersection of spaces. So it makes sense when you discuss convex sets to look to bring 2 hyperplanes for infinity and measure what is the width in this direction. Okay, 2 parallel hyperplanes for infinity. And the claim is that if the volume is 1, it cannot be that in all directions you have more than the width of a Euclidean ball of volume 1, which is square root of n. If you have widths more than square root of n in all directions, the convex set would contain a ball of volume larger than 1, which is impossible. It would contain a ball. Right? So it means that you can find a certain direction where the width is more square root of n. Okay. Right? And maybe I should write it down. The volume of the unit ball is roughly the volume of the unit ball is very small, and the volume of a ball of radius. Let me write it in some. So if I scale it by square root of n times some small constant, then it has volume 1. So you should remember this thing. A ball of volume 1 is large, root of n. Okay, so we found a direction where the width is square root of n, and then we just do Fubini. We look on all slices. The integral of the order of the slice is 1. The interval, this is square root of n, so one of them has to be at least 1 over root of n. So that's a trivial bound here. But somehow it was a subtle question, was not solved for some time. Just for you to understand the subtleties and complications in high dimensions, let me just recall or tell you about the spherical concentration of measure phenomena. So in high dimensions, if I look at the uniform probability measure on the sphere, then it is concentrated in somewhat unexpected places. So for instance, most of the mass of the high-dimensional sphere is located in a tiny neighborhood of the equator. If you look at x1 equals 0, this equator on the sphere, and you look at distance 1 over square root of n, a very small number in high dimensions, it captures half of the mass, and this means that when you think of high-dimensional sphere, it's not always a good idea to draw on the blackboard or on the computer or on the notebook, to draw like something like a 3D sphere or 2D sphere. Sometimes it makes more sense to think of it as this shape in high dimensions because the mass is close to the equator. So some peculiarities in high dimensions. Okay, so this is a slicing problem. I mean, if you think of some examples for the unit cube, you can get slices of 1, right? Volume 1 just one. For the ball, it's also universal. If the ball is volume 1, the central slices have volume roughly square root of E, which is universal constant. So in examples, it seems that universal constant is the right scale in this question. Okay, what was the context of the slicing problem? So Bourgain studied the maximal function operator associated with any centrally symmetric convex set. This is okay, and he proved that this maximal function operator is bounded in L2 regardless of by universal constant, regardless of the dimension and some symmetric convex set. And from this study, he reached the slicing problem that was seems to be much simpler, but no, it resisted his attacks. And fortunately, this problem was recently resolved, mostly thanks to the works of people like, so there were brilliant ideas going back to mostly to the PhDs of Ronen Eldan from Tel Aviv University in 2012, and they were refined by Lien Vempala, Chen and Guan, and others. And the final step in the proof was obtained at the end of 2024. So in joint work with Joseph Lehec from the University of Poitiers, we proved that this is indeed correct. For any convex body K in Rn of volume 1, there exists a hyperplane H in Rn, such that the slice of K with this hyperplane has volume which is at least universal constant. Okay, this is true. And in this lecture, I'll tell you, okay, so as I said, this is the opening gate to a better understanding of convexity in high dimensions. It's just an isolated statement. And I'll tell you in this lecture about connections and equivalent formulations, things like that. Now we have 3 proofs of this theorem. All of them use Eldan's stochastic localization from Ronen's PhD. But they have some differences. So there is a proof by Pierre Bizol from the Weizmann Institute. And there is another proof that we have with Joseph that gives something slightly stronger called thin shell and Zen slicing. And I'll discuss in this lecture mostly this proof, I think, in more detail. But still, all of these proofs use kind of very heavy machinery developed over the years and refined. And you know, this is such a simple statement. You could imagine that should be some direct, short proof. Nobody knows. Okay, so let me tell you another. Okay, so I'm going to tell you about quite a few connections of this slicing problem to different things in mathematics. Also, historically, so Bourgain really worked it as a question, or that he does not know the answer, but you can find other threads in mathematics that led to this question. And one of them is the Weizmann-Petit problem from the 1950s. So first of all, let me tell you what we know now, thanks to slicing. I think it's quite believable that if you have this theorem exists of one slice, you kind of can abrogate it to say something like this corollary. So as it turns out, if you have 2 convex sets in Rn, which are centered, I want their bias to be the origin. And now, let's assume that for any hyperplane through the origin, through the barycenter, the volume of one intersection with K is smaller, not larger than the volume of the corresponding intersection with T. Okay, so for each slice, it's like one volume is smaller than the other volume. Then the corollary is that the volume of K is at most some universal constant times the volume of T. Okay, so maybe a priori, I mean, constant depending on dimension is easy in these things, but universal constant is difficult. And for many years, so this originated from a theorem, from theorems by Weizmann and Petit. Okay, I got it. I just stand on this cable. That's my. I never stand on it again. Sorry. So yeah. So the Weizmann and Petit problem. So Weizmann and Petit proved that this is true with C equals 1. So we don't need this constant in many cases. So they only consider the centrally symmetric case, and they prove that if K is a Euclidean ball, it's true with constant 1 for any T. Or if K is a cross polytope, L1 ball, it's also true with constant 1. And the conjecture is true always. And there was lots of research, and in the end, what we know is that C equals 1 holds true only if n is at most 4. So up to 4 it's true, false up for n larger than 5. And in fact, geometry in high dimensions is so non-obvious that the counterexample in high dimensions is just the cube in the Euclidean ball. So this was proven by Keith Ball in the 80s. If you let K and K, so I told you that if K is a ball, it's always correct. So if T is a ball and K is a cube, you lose the constant factor. Okay, so this also shows that indeed, this up to universal constant is the right scale in this business, so it seems. That's the volume of sections are kind of determined up to universal constant by some global information. Okay, there is another way to look at the slicing problems that Bourgain promoted, which has nothing to do with slices. Okay, so it's slightly indirect. I'll explain how to connect the slicing of hyperplanes to this business with covariance. So the idea here is it looks different, but it will turn out to be the same. The idea is to look on two linear invariant ways to measure the size of a convex set. So if you have a convex set, the most natural SLN invariant way to measure its size is just the volume. The volume is a number invariant under SLN by SLN is a group of linear transformation of determinant one. So the volume is of course an invariant, but there is also another invariant which is related to the inertia ellipsoid, the Legendre ellipsoid of the convex set K. What is the Legendre ellipsoid of the convex set K? So it is an ellipsoid. You can find there is a unique ellipsoid, which is the second order approximation of K. If the Barrett center is a point such that for any linear functionals, the integral on K is the value of the Barrett center. If you take second order polynomials of degree 2, there is a unique ellipsoid such that for any polynomial of degree at most 2, the integral over the ellipsoid is the same integral over the convex set. It's called the Legendre ellipsoid of inertia, and you can look not at the volume of K, but at the volume of the Legendre ellipsoid of inertia of K. Or equivalently, it is determined by the covariance matrix. The covariance matrix is just the second matrix of the integral of xi xj. Let's say this K is centered, so we don't need these terms. Just the integrals of all monomials of degree 2, this matrix. And the determinant of this covariance matrix is another SLN invariant of the convex set K. And Lk, in Bourgain's notation, the isotropic constant of K, is the ratio of the determinant of the covariance. So if you want the square of the volume of the Legendre ellipsoid of K, to the volume of K squared. So this thing is invariant under all linear maps. The isotropic constant of a ball is the same as the isotropic constant of an ellipsoid, and the isotropic constant of a cube is the same as the isotropic constant of a parallelepiped. Okay? And it turns out, and as I'll explain in a minute, kind of the right way to think about the slicing problem, the one that has more applications, is in terms of Lk. The question is whether Lk is bounded from below and from above by absolute universal constant. This is equivalent to the slicing problem. So we know it. So thanks to Bourgain's formulation, we know that for any convex body K in Rn, this isotropic constant is bounded from above and from below by two numbers. So this means that the volume of K determines the volume of the Legendre ellipsoid of K, the second order approximation of K, up to some C to the n. Okay. The lower bound is an easy thing because it's not very hard to show that the isotropic constant is minimized for the Euclidean ball. And for the Euclidean ball, you can compute it, and I give the trivial lower bound, 1 over square root of 2 pi e. However, the upper bound requires that slicing theorem. Okay, so we know these things about Lk, determinant of covariance versus volume. Okay. Since we work with covariance, and I'll explain in a second why it's related to slicing, since we work with covariance, and with the Legendre ellipsoid of inertia, it makes sense to normalize the convex set and to require, for example, that its Legendre ellipsoid is a Euclidean ball. Or equivalently, it makes sense to require that the covariance matrix of K is a scalar matrix. Okay? And if this is true, if you decide to normalize the second order moments of your convex set, then the tradition is to call it isotropic. Okay? So this word, some people object to it because it feels, it's just a matter of normalization, and it feels like a strong requirement, but we will stick to it. So isotropic just means that we apply some transformation and transform the Gender ellipsoid to a ball. Okay? And the covariance is a scalar matrix. Okay? And under this normalization, you can have very clear understanding of hyperplane sections. Okay, so we'll see that the covariance dictates many things about hyperplane sections. For instance, for any two hyperplanes, so Hensley, this is actually basically goes back to Hensley in the central symmetry case. Before Bourgain, Bourgains were influenced by Hensley. If you take any hyperplanes, H1 and H2 through the origin, through the barycenter, they have comparable volumes. Okay, so this convexity assumption immediately gives you that any sections through the origin cannot have volumes that are too far from each other. For a general convex body, the worst thing is square root of 6, but in some examples it's better. For the cube, it's square root of 2, for example. And moreover, it was known to Hensley and to Fradelizy and to, but certainly to Bourgain, that the common volume of all of these slices is dictated by the volume of K times this inverse isotropic constant. So now we know that this common volume of the sections is roughly the volume of K to the right normalization. This is true for any convex body with a scalar covariance matrix. Okay, so now let me tell you how to prove this relation between covariance and volume of sections, because it's not obvious. And this is proven using the Bourgain-Minkowski inequality. So let me remind you about this classical Bourgain-Minkowski inequality. So this is a classical inequality proven by Brun in 1887 and kind of discovered by Minkowski and promoted, and they did many things about it. There is this Minkowski sum of two sets. This is the sum set. I take any point in A, any point in B, add them, and get A plus B. A good example is the take A and add to it epsilon times the Euclidean ball. So you take A and add to it all vectors of norm smaller than epsilon, which means that you take the epsilon neighborhood of A. That's a good example for Minkowski sum. And the Minkowski inequality just tells you that if you have any two non-empty sets, Borel sets, then their sum is actually a big measurable, and you can say that the volume of A plus B to 1 over n is at least the volume of A to 1 over n plus the volume of B to power 1 over n, and there is a quality when A and B are convex sets that are homothetic. And the nice thing about the Minkowski inequality is that in some sense, okay, isoperimetric inequality we have in any metric space with measure, right? It's something very general. But it turns out that in Rn, you have some inequality which is kind of elegant and stronger than the Bourgain inequality. So it embodies all information of the inequality in a better way. In fact, I don't know of any other geometry, not even a parabolic space or the sphere, we have such a nice inequality, which is kind of, when you use the Bourgain inequality on Rn, you better use Minkowski in some sense, and don't have such many other geometry. Let me tell you why Minkowski immediately implies the isoperimetric inequality in Rn. Because of the following. If I have two sets in Rn, no, if A and B are, if A is any set in Rn, I can take a ball, Euclidean ball of the same volume as A, okay? Then, if I look at the epsilon neighborhood of A, which is this set, by Bourgain-Minkowski, it is at least the volume of A to 1 over n plus the volume of this to power 1 over n, okay? And we know that there is equality where the two sets are homothetic, meaning that since B is a ball, there is equality where A equals B. So I just got this inequality that the epsilon neighborhood of A has volume which is minimized, whereas the Euclidean ball, this is true for all epsilon greater than 0. And now, if A is a smooth boundary, okay, this is an assumption, and if A is a nice boundary, then you can take the limit to epsilon goes to 0 and say that this tends to the boundary, so you get the isoperimetric inequality in its classical form. Okay, so this requires some assumptions, but Bourgain-Minkowski requires nothing, just on empty Borel sets.
So what is Bn? Is it a unit ball?
Unit ball. I didn't say that. Oh my. Yeah. Thank you. Bn is unit ball.
B is a ball and B to the n is a unit.
Yeah, I already wrote it, and I wrote it, but did not type it. Yeah. So Bn is unit ball somehow. Yeah. And if I forget, Sn minus 1 is unit sphere also for me. These are things that I'm used to, but it's my idiosyncratic way of looking at the world. Yeah. So Bn is unit ball and Sn minus 1 is unit sphere. Okay, so how to connect covariance to volumes of slices? there is a basic corollary of the Bourgain inequality, which you can prove by looking at slices of a convex set, which says that if you have a convex set K in Rn, you take the uniform distribution on K, this is random vector X, then each coordinate of X, the scalar coordinate of X with any fixed vector theta, is a log concave random variable. And what is log concave random variable? Log concave random vector is anything which is supported in some convex set with density e to the minus h for some convex function h. Okay, so this just follows by the density is something, you say that it's a convex set, so the volume here plus here is larger than here. So you get that the density takes this form, a log concave density. And there are many examples for log concave densities, random vectors in Rn. Gaussian measures are log concave, uniform measures on convex sets, and it is a nice class of functions, log concave random vectors, closed under many operations. So if X is log concave random vector, linear image is again log concave. Weak limits, if they degenerate, if you have uniform measure on convex sets, and they become more and more thin and degenerate to something which is on lower dimensional space, it is still log concave. If you convolve to log concave measures, it's still log concave. Heat flow, everything, many things preserve log concavity. Okay? Moreover, Hensley has a lemma showing that in dimension 1, the situation is more or less like Gaussian. When you have a Gaussian, all you need to know is the expectation and variance, and then you know the Gaussian, that's it. In the log concave world, it's pretty much the same up to universal constant. So if you have, for example, in one dimension, log concave random variable, then the density looks like that. So it is centered at some point, let's call it, okay, let's say it's centered at 0. It is variance sigma, standard deviation sigma, and it decays exponentially like this. So it's at least, say, the indicator, at most exponential. Here it decays like e to the minus t over sigma. So it's a very rigid object. It's not a perfect Gaussian, but not that wild, okay? In particular, you can say that 1 over the variance is the value of the barycenter. You see from this picture, right? I mean, it's basically bounded from above and below by these things. And the supremum is also not, I mean, that's the way it looks. So you can connect for x theta, the value at 0 of the density of x theta is the volume of the hyperplane. So this is 1 over the variance up to a constant. So we were able to connect, by looking at x theta, we were able to connect volumes of slices, the value at some points of the density, and variances, and the covariance matrix. And from here, it's very simple to connect to get this Bourgain's reformulation, LK in place of slice, the volume of slices. Okay, now I keep saying, I think I said the word universal constant already 10 times in this 20 minutes. But what are these values of the universal constants? Unfortunately, our proof, all of the proofs that we have give constants that are too large. And it is conceivable that the truth is that the constants are quite small. It could be, so there is something called the strong slicing conjecture, which suggests that among all convex sets in the world, LK is maximized for the simplex. This is called the strong slicing conjecture. For the simplex, you get 1 over E. So it could be that this is the maximum value. And if this is true, then you get classical conjecture, the Mahler volume product conjecture, the fact that the volume of K in the polar body is maximized for the simplex. This is famous conjecture proven by Mahler in 2 dimensions in 1979. And if you restrict your attention to centrally symmetric convex sets, the strong slicing conjecture speculates or suggests or states that, that LK is maximized for the cube. And if this is true, you have another consequence, the Minkowski lattice conjecture, some certain classical conjecture about lattices proven in 2 dimensions by Minkowski in 1901. So this is still completely open. Okay, I don't think that our current methods are many, but I mean, it's not. Even in 3 dimensions. You're probably right, yeah. It's not known, yeah, probably right. Okay, if you kind of look at for the history of the slicing problem and equivalent formulation, so one nice historical thread is starting with a question by Sylvester. So there is I would not know about it if it wasn't for some survey paper by Pfeiffer. So there is apparently a question that was published by Sylvester in 1864, which is, I think, the earliest thing that is kind of similar to the version of the slicing problem. It's the following question. So let's choose 4 points randomly and independently in a planar domain. Then there are 2 possibilities. Either these 4 points are in a convex position, like here, or 1 point in the convex hull of the other points. And Sylvester asked, what is the probability that they are in convex position? Okay, and you can, for each, depends on the planar domain, you get some numbers. There is a nice corollary of the slicing theorem. So it was noted by Weizmann and Pajar in the 80s that and thanks to the slicing theorem, we know the following. So the n-dimensional version of Sylvester problem does not depend that much on the convex set in some sense. If you have any convex body, I need to select n plus 2 random points, IID uniform in K, then the probability for a non-convex position is pretty small. But so between these two estimates, 2 universal constant over root of n to the n, we have these probabilities. Why is that? Why do we have connection to the Sylvester problem? Because of the following, this is the proof of the connection, let me explain to you. So suppose you have n plus 2 IID points uniform in K, okay? What's the probability for a non-convex position? What is it? This is the probability that the n plus 2 points is inside the convex hull of the first n plus 1 points. Okay, I forgot. I normalized K to a volume 1. In this, I forgot. If the volume of K is 1, let's say, so this probability is just the volume of the convex hull of these n plus 1 points. Okay, and what's the volume of the convex hull of n plus 1 points in Rn? It's a simplex in Rn. So the volume is just a determinant. You translate this thing, and so that's the expression that equals P of K. So get rid of the n plus 2 point, and that's what I need. Now I'm allowed to replace the L1 average by L2 average. Okay, I'll explain in a second. And if I replace the L1 average by L2 average, I just lose a factor of 5 or something, and then I get the L2 average. And as it turns out, the L2 average just equals. So if you just play with the determinant, it's pretty simple. I mean, even AI can do it. 2 years ago it could do it. No, let's say 2 months ago it could do it. Then you get that it's LK to the n. Okay, so that's why that theorem about Sylvester problem is correct. You just need to replace L1 by L2 and observe that it's LK to the n. Why am I allowed to replace L1 and L2? Because of the following reason. Let's condition over everything except for x1. And let's look at the determinant, let's call it y. If you condition about everything except for x1, then the determinant y is some linear or affine function of x1, of the local random variable x1. And we said that, so y would itself would be also low concave. And for low concave random variables in 1 dimension, it's all look like that, so simple. So you can reverse the Elder inequality up to factor 5. This is this proof of Sylvester problem. Okay, let me also tell you another consequence of the slicing theorem, which on the one hand seems to be pretty strong. On the other hand, I know of no applications yet of this fact, so maybe you can tell me. If you can say whatever. So I told you we have this convex body K in Rn, and we have this Legendre ellipsoid. This, is, by the way, combines the slicing theorem with a beautiful large deviation estimate of Gilruis Paris from 205. So if you have a central convex body K in Rn, then take its Legendre ellipsoid and let's normalize it to have the same volume as K. Okay, so this is like the second order approximation of K. Now, what happens if you scale the Legendre ellipsoid by factor 5? So, as it turns out, it captures all of the mass of K, really everything, except for a tiny mass that remained. This follows from the slicing theorem. And this is a strength, at least formally, it's a strengthening of the Weizmann ellipsoid theorem, which tells you that you don't get, basically it's the same assumptions, and the conclusion is that, first of all, you don't know which ellipsoid, is that there is some ellipsoid, which is hard to describe, and you don't get something close to 1, you just get something which is at least half to the n, something that does not decay too fast to 0. But two things I have to say. First of all, we use Weizmann ellipsoid in our proof of the slicing theorem. So we cannot do anything without it in all proofs. Okay, that's one thing. And second, that theorem, although it looks weaker, it has quite a few consequences. The Bourgain inequality, reverse Bourgain-Minkowski, which I've said. This is nothing. So yeah, okay. So this is Weizmann.
What is C?
Universal constant. In this lecture, C is always universal constant. So that's really important. So C and C are universal constant always. And usually, let me tell you a secret. If I put capital C, it's constant larger than 1, and small c is smaller than 1. Between 0 and 1. So this is like half, maybe. This one is like a half, and this one is like 5. Like in your head. I mean, I hope. It could be, but like larger. Okay, I think I told you all of my secrets. The unit ball, the little c, the big C, I think you know everything about it. Okay, let me skip this. Now, let me tell you about the history of the slicing theorem, slicing problem. So as I told you, the relatively trivial upper bound is root of n. And Bourgain did n to the quarter log n, and for this used this things like this Talagrand majority measure, sub-Gaussian processes, and K-convexity of Pizier, which is really a gem of local theory of Banach spaces. Then, in my childhood, I removed this log n and got n to the quarter. And for that, we used kind of tilts, exponential tilts of the convex set, and this Paulus result and some result. So it seems to be a different proof than Bourgain. There was no Talagrand or convexity. Then, Lee and Vempala in 2016 used, so in the midway, in 2012, Eldan wrote his amazing PhD. So Lee and Vempala got another proof of n quarter, which used what I think is also a third very different proof. They used the thin shell theorem, which we'll talk about today, and a stochastic localization, and so the exponential tilts were replaced by Gaussian tilts. You have this factor here, but it's really a deep thing because the dependence on t gives you a whole lot of analysis. And you know, all of these three completely different proofs lead to the same n to 1/4, maybe up to log. So it could be that at the time, some experts thought that this is the truth because Bourgain tried and got n to the quarter. And this was the state of affairs. However, Yuan Zichen, fortunately, did not listen or did not pay attention, or just did not believe in this n to the quarter thing. And he just noted that you can modify this technique of a dust localization and get something which is better than any power of n. So e to the root log is much smaller than n to the epsilon for any epsilon. This was a great achievement and a breakthrough by Yuan Zichen. And for that, he analyzed this certain covariance process of stochastic localization in a better way, using some self-controlled way. Then the process was fast after that thing. So with Joseph Leck, we got a log to the 4, and then Leaves and Palin Petit got another log. And then in 2023, so we were able to avoid using Chen's gross regularity estimate and replace it by some Bochner formula and some positional inequality and get root log n. But then in 2024, King-Yang Guan brought back the Chen approach of self-controlled gross estimate of the covariant process, analysis of third tensor, and got log n. And more importantly for us, in the way to put this log n, he proved an estimate that when U would give the slicing theorem. So very quickly afterwards, we were able to complete this completely by using this breakthrough by King-Yang Guan from the Academy of Science in China, from the Chinese Academy of Science in Beijing. So this is the history of the virtual slicing problem. Now, let me tell you a bit more about the low concave case, the isotropy constant in the low concave world. Why I'm not happy with just convex bodies? Why do I have to pass to the low concave world? That's because all proofs are very analytic. You run the heat flow, you do things like that. You cannot stay in our proofs in the world of convex bodies, okay? Maybe that's another sign that the proof should be other proofs. So let me tell you the story from the beginning. How do you deal with isotropy constant? This time not of a convex body, but of a distribution, of a low concave distribution. So covariance and volume. How would you replace these in the low concave case? Covariance remains covariance. You still have the table of the covariance of the measure. But what would you do for volume? What replaces volume? Entropy. I mean, the volume of a convex set is kind of its entropy. So I take the differential entropy minus integral of f log f. And the entropy constant is entropy versus covariance. And this formula generalizes what you get in the case where you have the uniform measure on K. So now we can have isotropic constant for anything below concave. Now, entropy. What's the entropy in the low concave case? So the entropy in the low concave case is a very well-behaved object. So if your density is e to the, so suppose that the law of x or mu, so suppose that the law of mu is e to the minus psi, then the entropy of mu, let's say that x is density e to the minus psi, then the entropy of mu is the expectation of psi. So if you want, the entropy is a typical value of the function psi under this low concave distribution. And in fact, in the low concave case, there are quite a few ways to describe this central value, not just the expectation, but you can do many things. So you can replace the expectation by the infimum of psi, and is not that far from the entropy, or the value of the barycenter is not that far, would give you the same thing here. Or you can take even exponential moments of psi, not just expression, will give you all the same thing. And just because these things have really very short one-line proofs that demonstrate how to use low concavity. So let me prove for you just this item 1, for example. So how would you prove that the entropy, the expectation of psi is roughly the value of the barycenter and roughly the infimum? How do you do that? The first inequality is just Jensen. Since psi is convex, psi at the barycenter is smaller than the expectation of psi. That's very simple, which is the entropy. Now, how do you prove the second inequality? Let's take any point y in Rn, and let's recall that the convex function lies above its tangents. Right? The convex function is like this, so it lies above the tangent. So for any y, we know that if I look at the tangent at the random point x, I know that psi at x is at most psi of y minus this gradient. And now psi of y does not depend on x, so it gets out. And this thing here, if you integrate by parts, you see it has expectation exactly n, if things are smooth. So that's how you get the fact that entropy is a very stable thing, just a typical value of psi. That's what it means. There is also a result by Bourgain and Weizmann, which gives you concentration, very precise concentration estimates for psi of x. So this is why we like a lot entropy in the low concave case. It's a well-behaved parameter. And yeah, so the same thing, the same proof gives you that for any low concave measure, L mu is bounded by 2 universal constants. And in fact, here, the one over the lower bound is a classical inequality. This is attained by Gaussians. It is the fact that is familiar to many that among all distributions of a fixed covariance, entropy is maximized for the Gaussian. Okay, so that's this left-hand side here. When the upper side, it's universal constant, a large one, above 5, that's what we know. And yeah, we don't know the value of this constant yet.
The value you get is the same for as top one with one because you use this one, or do you get better?
Yeah. I don't have anything. Yeah. I don't have anything better in the convex set case. It's really the same. But really, it's in thousands. It's not a competitive value. Okay. Yeah. Okay. So now let me tell you about the 2024 proof of the slicing theorem. So this uses an idea of Bourgain and Weizmann from 2012. The idea is that we should analyze the isotropic. First of all, we are deep into the analysis world. We work with low concave distributions, Gaussians. We don't do anything geometric. We use analytic tools. And the reasonable analytic tools, of course, the heat flow in Rn. So you start with your low concave measure. You can convert it with Gaussians. Let it flow by the heat flow. And what does it make sense for this problem to try to analyze the heat flow evolution? For 3 reasons. First of all, heat flow in Rn, Gaussian convolution, preserves low concavity. Gaussian is low concave, and if you convolve to low concave measures, you remain low concave, okay? So it's a very natural thing in terms of convexity. Second fact is that if you convolve two measures, the variances just add. Just add the values of the variance of the Gaussian to the original measure. So the covariance changes linearly, and you can just normalize it out. So basically, the covariance say does not change pretty much. It's a very simple thing under the heat flow. That's the second reason. And third reason is that heat flow in Rn is also very it's great with entropy. So as I write here, meaning that you know that the entropy increases under the heat flow. This was known to Shannon already. So the derivative of entropy along the heat flow is the fission formation, and you could hope to try to analyze, to use information theoretic tools. In this case, we use the deficit in the Shannon-Stam inequality, and we analyze this deficit along the heat evolution, and that's how we prove this theorem. However, it's not. We don't know to, and it's not enough to. You'd expect that things would be proven using integration by parts, Cauchy-Schwarz, things like that, but it's not quite the case. The proof relies on quite heavy stochastic interpretation on the heat flow using Brownian motions, things like that. And we have to deal not with the first derivative of entropy and not even the second, with the third derivative. And we have third order tensors, so it's a rather involved proof. Okay. So now, as I said, there is the 2025 proof of the Slutsing theorem, which uses the thin shell phenomena, which we're now going to describe. Any questions, by the way, about this?
What is the constant in the slicing theorem that you get? Also small?
No, but bad constant.
Huh?
Bad constant.
Yeah. Sorry. You said we get n to the quarter times log n. Is
That's
that log n actually like the k convexity and you only use a k convexity is up or down strike?
Yeah.
Okay, or okay.
The log of distance Euclidean. You can replace the log by log n is, you can replace it by the logarithm of the distance Euclidean.
Okay, right. So okay.
Yes. So in the K convexity theorem of Pizier, there is an application, famous application of this K convexity theorem to bound the mean widths times of K times means of the polar body, and in that sense you have a log of Banach-Maslov distance to Euclidean, and he asked if I can improve this log n to log of Banach-Maslov distance to Euclidean. The answer is yes. In Bourgain. Yeah. Okay. Let me now discuss a different question, the variance conjecture or the thin shell phenomenon. Okay, so we have the following normalization, which says that X in Rn is isotropic or normalized if it is centered, and if the covariance matrix is the identity matrix. Okay, so we just normalize it, and of course, any random vector with finite second moment, absolute continuous, you can find in our map and make it Barrett center zero mean and identity covariance. Now, there is a strange phenomenon in high dimensions called the thin shell phenomena. And this is the fact that for many distributions, for example, IID random variables with finite second moment, you can tell that most of the mass of the distribution is concentrated in a thin spherical shell in Rn. So the width of this thin spherical shell is much smaller than the radius of this spherical shell. So this is true for independent random variables because sum xi squared over n tends to 1, and this if the IID and standardized, so this means that the norm of x is close to on a sphere. So for IID random variables, it's kind of very simple. But a deep conjecture by Antila Bonin-Privisinaki and essentially by Talmud and let's say officially by Bukovin-Kordovsky or formally by Bukovin-Kordovsky, stated that the same effect, that the mass is in a thin spherical shell, the same effect holds under convexity assumption. So they conjecture that for any Log distribution, if you normalize it to have mean zero and identity covariance, then the mass is concentrated in a thin spherical shell whose radius is roughly square root of n. This is dictated by the normalization. And the width is just a constant. The variance of the Euclidean norm of x is at most, oh wow, it's a universal constant. Wow, it's so, this is just no n. Oh wow, this is a trivial statement. This is universal constant here. Oh wow, that's embarrassing. So, okay, so we have to prepare the slides. So, yeah, so x, I just like again, x minus root of n squared with most universal constant. So the width of the Euclidean norm of x is bound by universal constant. Okay, and we know by our work with Eldans that this is actually so this effect is not true without log concavity. You can have uniform measure on two spheres, which is not considered on a single sphere. And we proved with Eldon that this conjecture implies affirmative answer to Bourgain slicing conjecture. Another important thing about the thin shell phenomena, and the reason why it was introduced, was that it implies central limit theorem for dependent random variables. So if you have random variables, some distribution in Rn, which is not low concave and not independent, just any distribution, then the property of having lots of approximately Gaussian marginals is more or less equivalent to the property of having your mass and thin spherical shell. So there is a theorem that was started by Sudakov, Diakon, and Friedman, and then these are Bubkovich, Yakov, and Getze. I will write their names in length in the next slide, which tells us that if you have a random vector in Rn, mean zero identity covariance, you have a positive number epsilon. Let's assume the thin shell condition. So 1 minus epsilon of the mass of X is in a distance epsilon from a sphere radius square root of n. So this is a thin shell condition, right? X over root of n is close to 1 usually. Then the conclusion is that you can have, there are many, many directions. There is a subset of the unit sphere, which is a subset of the good directions. The measure of this subset is very large, it's at least almost close to 1. And for any such good direction theta, the random variable x times theta is approximately Gaussian. So the Kolmogorov distance between x times theta and the Gaussian distribution is bounded by something depending on epsilon and on n, and it is small when the thin shell is good and when dimension n is large. So under thin shell assumptions, we have a central limit theorem for dependent random variables. And this is a nice proof using spherical and Gaussian or Gaussian constraints of measure in high dimensions. So this is why we're interested in thin shell estimates. Okay, fortunately here I quote it correctly. So our theorem is that if you have a local random vector in Rn of mean zero identity covariance, then indeed this holds true. And this is also tight because if you look for the Gaussian, for example, then you get roughly 1 here, okay? So there were many bounds on the way. So people proved C times n to various exponents. Fleury got 3 over 8. Gudon and Weizmann got 1/3. And then some better estimates by Liv and Pala got 1/4. And then Chen, Weirlake, and then at the end we got this constant after many years. And another thing that we know, not only we know that most of the mass is in spherical shell, but we also have some large deviation estimates that accompanies this thin shell bound. So in fact, if you apply this theorem together with reverse Helder inequality for polynomials, which is something go back to Bourgain in 91, and then a decade later, Carby and White and Azarov, Solin, and Volberg developed it. You conclude the following inequality. So the Euclidean norm of x for random vector x with this randomization is so close to square root of n that the probability it deviates from square root of n by more than t decays like e to the minus square root of t. So this is what we know here. There is a conjecture that the square root of t should be t, but we don't know this as far as we don't know it right today, as of today. Okay. So let's combine what we said. We said 2 things. We said that first of all, low concave distributions have their mass in a very thin spherical shell, as tight as the Gaussian. And another thing that we said is that if you have thin shell bounds, then you have a central limit theorem. And let me tell you what is the state of the art right now about the low concave or the convex central limit theorem. So actually the situation is pretty good. If I have a random vector x, which is isotropic in Rn, isotropic means mean zero covariance identity, and low concave, then you can find the subset of the unit sphere of good directions whose measure is least, let's say, 9 over 10. So most directions are good. And for any such good direction theta, the Kolmogorov distance to the Gaussian is roughly a constant over n, up to some log square factor. So that's pretty good. For the unit cube, you get constant over n. So only this log factor is missing, okay? And this follows by combining our result with those of both Kopchis, Yakov, and Getze, okay? And I should say that this was first proven in our work in 2007, and this was earlier conjecture by Telebon, Perisinaki, and by Bremen Fucht. Just without any bound, just the fact that there is a central limit theorem like this for convex sets. Okay, and also you can remove the log factor in some case. Let me skip that. Let me now just tell you some ideas from the proof of this variance conjecture, okay? So in order to prove slicing, what we did in 2024, we analyzed the entropy, the evolution of entropy along the heat flow. For thin shell, we do something else. For thin shell, we will use some ideas of coupling and transport cost. And let me explain to you these ideas. So first of all, let me introduce the L2 Wasserstein distance between two probability measures. What is this thing? So you look on all possible couplings of mu2 and mu1, so all possible random variables on a common probability space, where x1 is low mu1 and x2 is low mu2, and you want to couple them in a way so that x1 is usually close to x2. So you take the infimum over this cost, and the infimum is called the Wasserstein, the W2 distance between mu1 and mu2.
Is mu is the same as mu?
Yeah. Yes. Thank you. We use the same as mu. Yes. Yeah. Now, this is the L2 Wasserstein distance, and I'm interested in the infinitesimal version of this L2 Wasserstein distance. So I want to compute W2 of a measure and its small perturbation. So I take the measure mu, I take some function bounded of integral 0. So 1 plus epsilon f times mu is again a probability measure. So I can look at the Wasserstein distance of mu and 1 plus epsilon f of u and take the limit when epsilon goes to 0 of this quotient by epsilon. And this has a very nice interpretation. So this is actually the h minus 1 norm of the function f. It's the dual norm to the h1 norm, to the integral of gradient f squared. Okay, so this is this fact was known to Otto, and before that, it's pretty much in the first paper of Brenier on the optimal transport. So we have a nice interpretation of the transport cost as the h minus 1 norm of the function f, the inverse Sobolev norm.
U?
Yeah, so the sum of this expression over all functions u for which this integral is more than 1.
The function down in which space?
One? Let's take local Lipschitz function on Rn. Company supported smooth function in Rn. Okay, it's good enough. It's not it's dense in H1. This space is local. Okay. Now, so far we did not use any low concavity. It turns out that in the low concave case, you have something which we call the H minus 1 inequality. So there is some funny commutation between a gradient and H minus 1 norm. So it turns out that for any low concave, if we use low concave, then for any function f, its variance is at most the H minus 1 norm of the gradient. So you kind of take a derivative, so it's 1 over meters if you want, and then take the H minus 1 norm, so the things go up. And you have this inequality just in the low concave case. Okay, why would that be correct? This follows from the Bochner formula. The Bochner formula is a formula from Riemannian geometry, but it turns out that in this business, you have completely analogous formulas in the low concave case. Low concavity is just completely analogous to the fact that the Ricci curvature is non-negative in Riemannian geometry. And I'll explain in the next slide how to do this, the Bochner formula, and get this inequality here. Okay? But for now, let's just apply this H minus 1 inequality, and then we conclude that for any isotropic probability measure in Rn, if I look at the deviation of Euclidean norm from square root of n, by literal trivial inequality, it's most, no constant here, the trivial inequality, it's more the variance of x over n. And if I apply for this function x squared, whose derivative are known to me, we conclude that the variance of this function is at most 1 over n times the sum of the h minus 1 norm of the linear coordinates. That's what we get. Okay. Now let me do two things. First of all, let me tell you about the Bochner method and how could I relate variance to transport cost of gradients. H minus 1 is transport cost of gradients. And second, let me show you how to bound the transport of the gradient. So first of all, what's the Bochner method for Riemannian geometry, and how does it look in our context? So let's assume that our density mu is e to the minus pi for some nice function psi, smooth, I will not need anything else. Then I look at the Laplace type operator, which is associated with this function. Let me tell you what it is. So this operator appears in many places. It appears in Langevin, in Fokker-Planck. So I just take this is the definition. It's Laplacian, which is twisted by some first order term that is adapted to psi. And the reason why we define this operator is the following integration by parts. So we take the Dirichlet form. We take this. If you take two completely supported smooth functions and you integrate LU times V, you can integrate by parts and get grad U, grad V with a minus sign. This is true for completely supported smooth functions. So we get a symmetric operator with a large core, which is negative semi-definite. It turns out to be essentially self-adjoint, okay, with negative spectrum. But the interesting thing for us is classical integration by parts, classical commutation of Laplacian and gradient in this context of L and the gradient, which gives you this useful integrated formula that the integral for any such U, the integral of LU square is the sum of two terms. And in our case, in the local concave case, both of them are non-negative. The Hilbert-Smith norm of the Hessian and the curvature term. This is like the Ricci term, Hessian of psi, grad U, okay? So this you can prove, not so difficult. It was known 8 years ago and even more. Now, if you just erase this term and apply some dualization argument, you get that H minus 1 inequality that I told you about. So this just follows by looking at this inequality, the definition of the H1 norm, and H minus 1 norm, and little games. This is what we get. This is how we get the H minus 1 inequality. Another important fact that was known to Ishnerovitz, essentially known to Ishnerovitz in the Riemannian setting, is that if you not only assume that the measure is low concave, that psi is Hessian of psi is non-negative, but you actually assume more, you assume uniform low concavity. You assume that the Hessian of psi is at least some number t. Then you get some Poincare type inequalities depending on t. Okay, so this is something that will be used more tomorrow. Okay, so to summarize, we know that we have some way to reduce proof that the variance of some function is small by proving that some transport cost of the derivatives are small. This is only the local case. So the thin shell, the variance conjecture follows from the following theorem. So we claim that we can couple, we claim that the H minus 1 norm of all of the coordinates, if we sum this, it is at most a constant times n. Okay, so for any local measure topic, we have this bound here. Okay, so this means that we need to construct some coupling, right? I mean, how would I prove this theorem? I need to tell you why the H minus 1 norm of the coordinates is bounded. And right now, we only know that the sum is bounded by constant times n, but we conjecture, it follows from something called the Cayley's conjecture, that each of these terms is at most universal constant. With this, we don't know. We only know that the sum is bounded. And what remains to be done is to couple the measure mu and the measure 1 plus epsilon xi times u at a very small cost. This is the meaning of this H minus 1 norm. Coupling, which does not move points too much. Okay, so you need to bound the certain distance, and there is a beautiful theorem by Bernier, which characterizes the optimal way to couple two measures so as to minimize the Wassermann distance. There is a gradient of convex function. It's a celebrated result. But somehow it's kind of, we could not analyze it at all. So the optimal coupling, just how to analyze for us. So we do something else. We construct another coupling which does the job. The Bernier is you know the way to use it. What do we do? So first of all, it's a bit annoying to look at 1 plus epsilon xi. I mean, for example, if u is not completely supported, this is not a positive function. It could have a negative weight. It's not a measure exactly. So it's much more reasonable to replace 1 plus epsilon xi by e to the epsilon xi. This makes more sense. In other words, rather than coupling these linear things, we couple exponential tilts. So we take our measure, mu, and for some y in our n, we add some e to the y dot x minus some normalizing factor. lambda of phi, then always the factor lambda y is the log Laplace transform of u. Okay, so we want to couple the measure mu with some exponential tilt. If you want some infinitesimal exponential tilt. What we actually do, we don't just couple the measure mu to exponential tilts, but we couple all exponentials between themselves. So we do the following thing. So there is a procedure that was appeared in several places in mathematics. It's called the Follmer drift. It appeared in a theory of nonlinear filtering and stochastic organization of Eldon. So this is a certain procedure that gives us simultaneous coupling of all exponential tilts of a given measure. So let me tell you how it works. So first of all, I need some definition. AT of y is the barycenter of a certain tilt, Gaussian tilt of the measure mu. Now the claim, the proposition that was known in the nonlinear filtering theory for many years is the following claim. There are two things that have the same law. So let me fix some vector y, some tilt y. Let xy be a random vector whose law is the tilted measure. Let me now construct for you another way to, let Wt be some Brownian motion in Rn, independent of xy. Then the following two processes with exactly the same law. The first process is just the process where you look at t. You start with a fixed vector y. Then you look at Brownian motion plus t times this constant vector. So you have a linear drift t times this fixed x plus Brownian motion. This is this process. And the second process is basically the conditional law of this given its own sigma algebra. It's set at t of y, and if you do the computations, you get that this solves the following stochastic differential equation. So it is just Brownian motion plus drift, which is exactly this function here. So there is a nice proposition that tells you that these two processes have exactly the same law. And this has a nice consequence. So this process here does not depend on xy at all, right? So it just depends on the starting point. If I start at y and run this stochastic differential equation, at time I get this process here. So for example, if I divide theta t by factor t, at time infinity, this goes to 0, this goes to 0, I'm going to get x. So this means in particular that if I look at option 2, if I start at time 0 at the point y, the limit distribution, this has a limit, and the limit has law mu y. So just this dynamics, depending on the starting point, gives you different tilts of the original measure. So this gives you some simultaneous couplings of all the tilts, and we analyze this thing and manage to prove this theorem. So my time is up, so thank you very much for your attention.
Any questions?
Thank you for a great talk. You mentioned that you were not happy, so to speak. No, you mentioned you were not happy with the constant you obtained at the end. Do you mention the nature of the constant? Like, is it implicit?
No, yeah. It is effective. Yeah, sure. It's It's not. There's no compactness argument at all. It's like no.
It's a number. Okay.
Yeah, it's just a number. Okay, we can give you the number, but it's too big.
And where would you say, what step in the proof would you say is where what you might suggest is the lack of optimality of that constant comes from?
So many steps, and
okay,
it's really too.
So there's multiple places. There's not like a
it's not
break.
just one place. It's all over the.
Okay.
We are not even. Yeah.
You said that the simplex had 1 over e.
Yeah.
If I can show it for a specific space, does that tell me something about that specific space, or is the
Again,
thing
if you should for some fixed dimension?
some fixed?
Yeah, this is in each dimension where you can prove that this is true, then you get the Malloy conjecture in that dimension.
For that.
For that dimension.
Okay. Oh, okay. Thank you.
Thanks for a great talk. Can you tell us how your 2025 proof relates to the prior works that you mentioned?
Yeah.
So I didn't see any third derivatives.
Yeah. So the 2025 proof uses these coupling things, and this process is one way to look at it is through a dense class localization. Okay. And now, in order to so how do you bound? The main thing is, so I told you what is the coupling, but I need to tell you about the transport cost. Okay. So what's the transport cost? So you need to understand how you have this stochastic evolution, You need to understand how far points are from each other. So let's look at it so the local derivative, okay, will be some matrix, and the evolution of this local derivative is a product integral, okay, of a matrix of the covariance process of stochastic equalization. So this is what happened. So this process, the way the things change here is product integral. You know what's product integral? Product integral meaning that you solve empty dot equals, it's matrix. There is some matrix, some covariance of some measure, whatever, and you solve this equation. This is called product integral, okay? And this process AT, this is called the covariance process of stochastic equalization. Okay, so this is if you want the second order derivative of things like entropy, you get these things. So and now we need to use some results about the growth of this covariance process. And this covariance process was the subject of investigations very elaborate by King Yang Guan and by Yuan Zichen, and by actually it started with Eldon himself. And they differentiate this covariance process, got a third order tensor, and add some bounds for that. And this was just used for bounding the trace of empty square. So we don't know that empty, we can just prove that the trace of empty square is bounded, which is exactly the average, the sum of the all transport cost. Because we had the trace of it. This is the way we proceeded.
Was the innovation in studying how AT changes over time, or in this part?
What?
Was the innovation in analyzing how AT changes, or in this setup?
Mostly in this coupling thing, and also with this relating the product integral to AT. So it was, we needed to use this constant inside this product integral. Also, okay, we had to tweak Guan a little bit. There was a little tweaks that we had to do for the Guan. Right. It was not, you could not just plug and play. We actually reproved. We had to reprove everything and change the proof a little bit. But really, the ideas are from Guan. What we did is just, we had stopping times, things like that, and we had some, improved the variance, and we had to do self-estimates and tails. But basically, these are mostly, these ideas are mostly from Chen and Guan.
One last question.
Okay, yeah, kind of a dumb question, but for the slicing problem, is it obvious that there is a constant upper bound? Because you mentioned something about concentration of measure for high.
Constant upper bound for what?
For the slicing problem?
This one?
Yeah, like how sure are you that you cannot replace the C with?
So first of all, if you want an upper bound here, okay, thank you. So if you want an upper bound here, so first of all, let's only look at sections through the barycenter, because otherwise you can get zero measure. Okay.
I guess my question is like,
let me tell you what's known. So if you, there is always it's true. So it's much easier to prove that there is a section through the barycenter, which is at most a constant. That's much easier than the lower bound. That's.
I guess my question is like, how sure are you that you cannot replace C with a C times square root of n on the right hand side? Like
no, no, it's not.
Like, is there an example for which like any section?
For the cube, for the ball. What's the cube and the ball, for example?
I mean, you measure spherical concentration measure, right? So if you slice through the center, doesn't that?
So let me tell you, if you have a ball of volume 1, the maximum slice is square root of 3, roughly. If you have a cube of volume 1, the maximum slice is square root of 2. So they're just universal constants, and you cannot go above.
I see. Okay.
Okay, let's no, it's the last question. So let's thank Boaz again.